Good afternoon, everyone. Welcome. Thanks for coming. For our speaker today, Youngho Seo from UCSF is known to some of us for many years. I certainly know him for many years. And I'm really glad that he's here because we really would like to extend our collaboration with him at UCSF in the future, whether it's in teaching and in research. So certainly for a student that should be of interest, because that's certainly what we hope to do. We can strengthen the collaboration. So Professor Youngho Seo is a professor and director of the nuclear imaging physics in the Department of Radiology at UCSF in China Basin. So not really far away, just one ferry ride over. He's professor in the Department of Radiation Oncology, faculty, affiliate at the Bekar Computational Health Sciences Institute, and program member at the Helen Dillard Family Cancer Center at UCSF. He's also faculty at the UC Berkeley UCSF Bioengineering program. He's also a scientist at LBL, and as you can tell, what's missing affiliation with us. Right? So that's what we want to achieve. Right? So be nice to him. So he has quite a few people in his field. His background is in physics. So he got his undergraduate, as a matter of fact, from Korea in physics on radiation effects, not in humans, but in electronics devices.
Satellites.
Satellites, I mean, of course. Then he came to the United States to get his master's, two of them, in physics, Alabama, and then at UCLA. At UCLA, he also got his PhD working on cold dark matter experiments using a dual-phase TPC.
Xenon.
Xenon TPC, of course. So, and then he slowly moved into medical physics imaging when he came then to UCSF in medical imaging, and that happened 2003. So the last 15 years he has been in medical physics, starting with a postdoc there, and now he's professor. So that can happen. Right? 15 years later, you started as a postdoc, and then eventually you become professor. He started under Bruce Hasegawa in 2003. Really one of the leaders in our field at that point. Unfortunately, he passed away exactly 10 years ago, Bruce Hasegawa. And I certainly see Youngho as one of the successors of him. So to continue the tradition, which Bruce Hasegawa started again a long time ago. Okay, so I think that's all I want to say about about our speaker, and he will talk about his research, what he's doing right now, and he has a lot of projects ongoing. But overall, I think the title captures what he's doing: quantitative molecular imaging using ionizing radiation. Youngho, please.
Thanks a lot for kind introduction. I'm really happy to be here. You can hear me well.
Okay.
So today, actually, I'm doing some experiments because instead of really talking about details about a few projects, I try to actually present almost one slide each for one project. So I have about 20-something research projects. So that's something you will realize. And the first thing I want to actually very much emphasize is that I want to actually give you the instrumentation and the physics research using gamma ray and X-ray imaging technologies. So in the medicine, especially in radiologic imaging, what I'm talking about is SPECT and PET, the imaging modalities. A little bit of X-ray there, but I'm not going to talk a lot about X-ray today. But these molecular imaging modalities like the SPECT and PET provide, really literally the quantitative information. But what if, we look at all of these imaging modalities from the user end, meaning, a lot of actually MD radiologists, use these imaging instruments to make medical diagnosis. But as a physicist, I happen to be actually in a lot of this clinical and also basic science, more like a biological-driven, the imaging applications area. Biology meaning, we use the small animal models and then we use imaging instruments to get quantitative information about the disease and making that, really use of trying to correlate that into actual disease outcomes. So studying challenging applications, I could see that what areas that we have to actually devote our time to do further development. That's what I'm going to talk about. So, really application-driven technology development is the focus. you'll see, what I'm going to talk about. The first thing is start of the SPECT CT. So I'll talk about 3 different categories in terms of applications. SPECT CT is one, and the next is PET CT, PET MRI, and the last thing I want to talk about is some of this newer technology, machine learning, deep learning areas. So using SPECT CT, the first application that I was involved in, so all the applications I'm showing is something that I either personally did as a member of a big group, or I led as a PI, principal investigator, to actually get the applications done using these imaging modalities. The first one I want to talk about is myocardial perfusion SPECT imaging. This is heart imaging, heart scan. But when we look at the heart and we really, look at this heart quantitatively. So what we are trying to see is this left ventricular myocardium, the heart muscle around the left ventricle. Using SPECT myocardial perfusion imaging, what we are again looking at is how perfusive this muscle is. This is the major heart muscle that pumps all the blood from the chamber out to the whole body. So this muscle should be very perfusive. Without the perfusion supplied to the heart muscle, cannot be really functioning very well. But using SPECT, it's really hard to do this type of imaging very quantitatively. To use SPECT, any radionuclide imaging, like a SPECT or PET, for any imaging, the signal we are seeing, in this case, I'm showing in this diagram that tracer uptake level is exactly the intensity of signal you can get from this SPECT imaging modality. If we want to look at the perfusion, the basic principle, the property of the perfusion is the flow, myocardial blood flow. Blood flow in the muscle, heart muscle, should be correlated with your signal in the imaging system. That's a connection I'm making here. But for the SPECT imaging, we have to use something that SPECT instrument can see. So technetium-99M labeled sestamide, phosphine, these are molecules we are using for the SPECT imaging of a myocardial perfusion. But as you can see from here, this flow is correlated with the tracer uptake level. But these 2 lines here are the sestamide and tetraphosphine. They are not actually making good linear correlation between the flow and then the uptake level. Meaning that, what if we want to do quantitative measurement using SPECT imaging of actually myocardial blood flow? Then what you get is this one. You want to deduce the information of flow from this information. It's really hard to do it. So what we are doing about this one is that we want to capture the perfusion, the signal dynamically using SPECT. This is a really challenging problem because the SPECT modality, imaging modality, if you want to do dynamic imaging, for dynamic imaging of a radio tracer like tetraphosphine or sestamide, you really have to have this SPECT imaging done in few seconds in the beginning, because when you inject anything intravenously, it moves very quickly in the beginning. It goes to the heart, right, then goes out to the lungs, and then coming back to the heart to everywhere. But that tracer, the molecular, basically any molecule movement intravenously, is going through blood circulation. It's very fast in the human. So we have to capture the data very the fast in the beginning, because that's when the tracer is moving really fast. But using SPECT, because we have the instrument that has to rotate around the human body, the heart. But rotation is slow. You cannot really rotate really fast. So getting full SPECT data, meaning full rotation of the camera, it takes time. So if you want to capture every 5 seconds of data, every 10 seconds of data, that's what we want about doing dynamic heart imaging using SPECT. Okay, so our collaborators, and then this is actually, initially the work from Dr. Grant Gerber, who's a longtime colleague, who used to be at the lab, now working with us. We are actually doing dynamic myocardial perfusion imaging using SPECT, using actually, projection-based the kinetics estimation. So this is really, I cannot really say about that, but what we want to, all the details. But what we want to get is that the tracer uptake, the level of the signal in the different parts of the heart, this is what we are looking at over the time. So this can be done, a lot of technical development. Okay. So here is the real application. Because when we can do dynamic SPECT myocardial perfusion imaging, what we can do is that using that technique, we can derive some of real quantitative values that is clinically relevant. MBF is myocardial blood flow measurement here. Using myocardial blood flow measurement, if you do this the heart scan with the stress condition. So what we want to know is that if the heart is functioning when heart is stressed. The heart is pounding very rapidly when we are putting some stress on it, like running or some pharmacological stress. Some drug actually can make a heart beating much harder. So if you can make a heart beating harder at the stress condition, measure myocardial blood flow, which should be higher. The flow should be higher compared to heart is at the resting stage. So if you compare these two values at actually the same value, but at the stress condition, at the rest condition, we can derive another clinically relevant the parameter called coronary flow reserve. This is very good parameter you can get. It can have a lot of clinical the inference from there, but it can be done only using dynamic SPECT and PET. Okay? This is also kind of the work showing that, okay, this is a SPECT technique using tetraphosphine here. We have done the same study using dynamic PET studies using ammonia. So we can make some comparison with them, and then we can actually deduce our measurement with tetraphosphine could be as accurate as the PET measurement, another imaging modality. So this is a further analysis about it. Now I'm switching to totally different project. I'm talking about cancer here. So we want to use our SPECT-CT imaging modality quantitatively. Quantitation, right? Quantitative imaging, making it accurate is all the things I'm going to talk about today. Now, what is it about quantitative imaging for the cancer? For the cancer, sometimes you want to know a lot about cancer. When people have cancer, we want to do some imaging. But what if we can do very quantitative, physically accurate measurement of a radio tracer uptake in the cancer? What if that radio tracer is actually very specific to the progression of the cancer? For example, the grade of the cancer. Tumor grade is the word I'm using here. Tumor grade could be very aggressive, very less aggressive, whatever. Tumor grade could be really. So when people have cancer, the cancer cells could be replicating very rapidly, or sometimes it's replicating very slowly. This is really about the cancer differentiation is actually pathologists use. So the hypothesis here is that when we can measure quantitative tracer uptake using SPECT-CT, can it be correlated with the pathologic grading of the tumor, the cancer? So we have done some imaging, but in here what we have to do is that the SPECT reconstruction algorithm, all these colored images about SPECT, the tracer uptake, that the image reconstruction algorithm should be very physically accurate. So we actually made a lot of corrections to the reconstruction algorithm. At the end, we felt that the current reconstruction algorithm we are using at that time could be quantitative to measure exactly, physically accurate tracer uptake in the body. So the next thing we did was that, this is actually prostate cancer patient. This is actually prostate cancer right there. The signal intensity from the quantitative SPECT measurement, is it really correlated with the pathologic tumor grade? This is the tumor grade for pathologists. So this is actually before the cancer was removed. This patient went through the surgery after the imaging. So we got the imaging data, we quantitated that data, signal intensity, and then after the surgery of removing this prostate gland, pathologists read the pathologist slides. They graded about how really aggressive the cancer is. So this is my result. This is a lower grade cancer, this is higher grade cancer, and then the signal intensity is distinguishable. This is not final result. This is one of really the first studies of this kind. From quantitative imaging data, we could get some of this pathology information even before opening up the body. Next one is also the cancer imaging application. This is again the prostate cancer. What I'm showing here is the sulfur colloid. This is colloidal particles. This is the sulfur colloid. It's the size, the size of the sulfur colloid here can see is it's very small. This is nanometer scale, 200 nanometers at this scale. So a lot of these colloidal particles, actually most of the colloidal particles, sulfur colloid here shown is about 30 nanometer size. When the particles, colloidal particles of that size, and then this is now, radio, so technetium-99m could be labeled into this. So we can make this sulfur colloids to be radioactive. With technetium-99m, we can image it using SPECT or in any camera. What it does is that if the sulfur colloid is injected to primary cancer, that cancer could be prostate cancer. Actually, more commonly it's injected for breast cancer or melanoma. But if we know primary cancer site, if we can inject radio-labeled nano sulfur colloids into that, what it does is that this colloid is spreading through the lymphatic system from the primary cancer. So it can go to the lymphatic system, and then for this size, it tends to accumulate at the first landing site. This is a lymph node we are talking about. And that lymph node from primary cancer is called sentinel lymph node. So this is sentinel lymph node imaging. And when the lymph node is harboring cancer cells, and it's usually disrupted, and the lymph nodes tend to accumulate more of this sulfur colloids. So higher uptake of this sulfur colloids in the sentinel lymph node could indicate that that could be harboring a lot of cancer cells. This is actually finding that if the primary cancer has spread to the first lymph node. Right? This is very good information you can get. So using that, so why actually, this is something that the hospitals just do, the medical doctors would do, right? But why I got involved into that is, it's prostate cancer. In fact, this type of work was never done before. And our prostate cancer, physicians wanted to do something like this because we are doing the same thing for breast cancer and melanoma all the time. Well, why not prostate cancer? There's a good reason for that. I mentioned about that this should be injected to primary site of the cancer. Prostate is not, superficial. You have to have someone to inject. So what we do is that with the ultrasound guide, somebody has to put the probe through the rectum, and then the prostate is all the way down there. People have to know how to put the needle into that, inject this. But this is very, the injection was done by very skilled urologists. But we were able to do this study, and then we did also SPECT imaging of that radio labeled the sulfur colloid. This is the imaging, one of the patient images. So as I told you that this high uptake area is actually the sentinel lymph node. And from this imaging, I cannot make medical diagnosis, but this could be also the sentinel lymph node that could have some cancer cells, potential. Okay? Why quantitative imaging here is important? It's not about quantitative imaging. What we realize is that when we develop this quantitative SPECT reconstruction algorithm, we could achieve a lot better imaging quality. This is pretty high resolution in terms of SPECT imaging. So we could more pinpoint where the sentinel lymph node was from this technique. That's how I got involved in that project. So just wrapping up about my SPECT discussion for instrumentation research. This is one point that I'm, preaching. Not I'm preaching, but our group, with Bruce Sasagawa and many people, working at that time, we knew that SPECT could be very quantitative. Why actually making this statement? Because if you just ask any nuclear medicine doctors, if they got traditional training, they'll say like this: PET is quantitative, SPECT is not. Okay. But SPECT-CT, when we have a CT, that actually helps about doing this very physically accurate SPECT reconstruction. We can make a SPECT-CT as quantitative as a PET-CT to some degree, maybe not, but it is very quantitative technique. SPECT instruments. So another thing that this controversy, it's not controversy, it's argument between the PET people and SPECT people is that all the people who know about the PET-CT, PET-MR, they like PET images because it's a lot cleaner. and then a lot of times it's a higher resolution. So that's by realization. We made a lot of effort to make a SPECT quantitative, but still, even that awareness is not everywhere. We are still making that effort. Companies make that effort as well. They're finally trying to market SPECT as a quantitative imaging technique. Finally, this is happening in the last few years. We have done this type of work already 15 years ago. Okay? That's kind of disconnection we are talking about. Same thing. We can make actually SPECT images look much nicer, but again, sometimes it's also related to insufficient hardware. So I realized that SPECT instrument, that is basically gamma camera, could be improved in terms of generating better images, better spatial resolution, better sensitivity and resolution. The key is that there is a common sense of there is trade-off between sensitivity and resolution. So I'll actually talk about this very briefly. And another thing that people also do research about SPECT instrumentation is that it's kind of fashion to make a SPECT instrument to be organ specific, because gamma camera is bulky, and then we can do like bone scans. This is used in nuclear medicine clinic. We have to have a regular SPECT instrument. But newer technology development for SPECT instrumentation is focused on making it smaller or just one organ only type of scanner. So there are commercial scanners made for SPECT system just to look at the heart. There are some commercial systems made for just looking at the brain. But I felt that if we do that, that means that we are just basically restricting our imaging instrument to just one application or just two applications. Why people have done that? If you actually focus on one organ, you can make a pretty high resolution SPECT system. That's why people have done that. But if we can have technology that we can do flexible geometry, and then we can have no trade-off between the resolution sensitivity, but can image the entire body, that will be actually the revolution that we can make. That's what I'm thinking. So, no trade-off between the sensitivity and the spatial resolution. That's what we are focusing on. So what we realized is, again, that we want to use the best possible currently the SPECT like detector material. So gamma camera can be built with the sodium iodide with the photomultiplier tube. That's a technology built in Berkeley 70 years ago by Hall-Enger. It hasn't changed. But we know that some solid state material like the cadmium zinc telluride is better, and it's actually getting better in terms of supply. People are making a lot more CGT material than before. In fact, when people were excited about CGT for the gamma camera, it's already 20, 30 years ago, right? It's something like that. But the implementation of CGT material into the gamma camera is not widespread, mostly because of price issues. It's good material, but if you build a huge scanner, right, it costs a lot of money. But this situation is getting better. CGT is getting cheaper, and people know how to make it actually much better than before. So we just invested our money into building CGT-based the gamma camera. CGT is really great in terms of getting very high resolution. I think you heard about this from other speakers in nuclear engineering. But with higher energy resolution, you can actually reject a lot of unwanted signal. That's how you can actually keep good sensitivity and then make actually imaging clearly, more clearly. So using CGT material we built together, this is a project that we are actually we built kind of a very simple collimator. But the design principle here is that we want to have this collimator hole to be exactly matching the pixelated CGT material. So this CGT material has a pixelated structure. So we want to just place our holes over the pixel, each pixel, so that we can maximize the sensitivity. We are not losing actually the sensitivity by blocking some of the sensitive detector material. That's our design principle. Another thing I want to emphasize is that people have done this one, not actually this one, but people have made CGT-based gamma camera. But they actually built CGT-based gamma camera for one application only, I told you, brain or the heart. But here, I want to use as a general purpose, really the CGT-based gamma camera. So this collimator can image many different radiopharmaceuticals using SPECT imaging. Could be multi-application application. Okay, the instrument. So we have built some mini camera. This is actually manufactured collimator, CGT material, electronics built. And then the next, actually, an effort we are making is that we make this to be big human-sized, the system. This is our design, the schematic right now. So instead of building, two separate gamma cameras, like large enough, and then rotate each other, what we want to do is that we make a kind of ring-shaped geometry to look at the organ by the detectors at the same time, so that we can achieve best possible sensitivity of looking at that. But another problem that I see that is that if we have one gamma camera like this one, the field of view is limited by where the collimator is looking at. So what if we want to build, actually look at the larger area like the body, the torso? The gamma cameras, like each individual cameras, could be axially, radially located farther, so we can look at the larger area. This can be done mechanically very easily. So this can be done actually. So this is what we are doing at the moment. Really inspired by kind of application has to do with the SPECT imaging instrument. Questions?
Silly one. What does SPECT stand for?
Single photon emission computed tomography.
Single photon
emission computed tomography.
emission.
It's a CT
tomography.
technique, but we are just looking at the single gamma.
Computed tomography.
Yeah.
Okay, okay. Single.
I think most of, do you have some imaging background? Anything, have you heard about CT, SPECT, PET, right? Yeah, that's what I assumed. Yeah. So that's why I'm really getting into the application directly here. So now actually I'm going to talk about PET. Okay, PET is also very exciting. So this is my kind of beloved project. And you can see that I even make the color of the font a little different here. You'll see this pattern later. Now I'll explain why I actually did this. But this is I-124, iodine-124, the meta-iodobenzoguanidine. This is a molecule labeled with iodine-124. This is the same structure as iodine-123. Any iodine here could be, attached there. The reason I'm showing this slide is that this one particularly can be imaged by positron emission tomography. This is a commercial product. You can just buy it. This is not a commercial product. You just have to make it. Okay, that's the real difference. Another difference is that this can be done by SPECT imaging instrument. This can be imaged by SPECT. This can be imaged by PET. So I'm actually just making the PET radiopharmaceutical into SPECT radiopharmaceutical into PET radiopharmaceutical. Exactly the same, because chemically there's nothing different, right? This is different isotopes. What does it do? So using iodine-124 MIBG PET, this MIBG meta-iodobenzoguanidine is norepinephrine analog. What it does is that it goes to where the norepinephrine transporter is. I don't think it really makes sense to use that much, but it's really good cancer imaging agent, or it could be also very good, the heart imaging agent. I'm focusing on cancer here. And another thing I'm showing, the word neuroblastoma. This is pediatric cancer. Also, this is also very confusing to everyone, a lot of people. Neuroblastoma is a very common, third most common pediatric cancer. That doesn't mean that it's common, because the pediatric cancer itself is not that common. Third most common doesn't mean that it's a lot of cases. I think we are talking about 600 to 650 cases a year in the United States. But that is third most common pediatric cancer. Another confusion about this word neuroblastoma is that when you see neuro, the neuro means brain, right? But neuro doesn't mean actually brain. This is nervous system. It could be any part of the central nervous system. Neuroblastoma commonly occurs in the abdominal area, not the brain. So this is the most common extracranial, so outside the brain tumor cancer in the But it does have very good uptake of this molecule, because neuroblastoma tumor does have a lot of norepinephrine transporter. But making the new radio tracer is not easy. There are people like Rebecca here is making also the radiopharmaceuticals. But I'm not a chemist, So I need a lot of help. But when we had this kind of push, this is not also not my idea. I heard from somebody else, but somebody else it couldn't do it because just doing something new, you gotta have all the resources to do it. But I got so much into that, I wanted to figure out how to do it. So the cell studies to see that this acts like actual MIBG. So we use the cells that we know that MIBG should be accumulated. So this is showing that actually these cells do not show any uptake. These cells do show the uptake, meaning that what we made was working. We did animal studies. This is really the very conventional path of developing new radiopharmaceuticals. We made it. Cell studies. This is animal studies. What you are seeing is that this is the tumors inserted to this mouse. So there's tumor cells, neuroblastoma cancer cells in the kidney of this mouse. So we injected, and then you're seeing the time course of the iodine-124 MIBG uptake in the body. This is dynamic imaging over 5 days. It's not like continuous imaging. We just image multiple times over 5 days. I'm showing the time course of activity distribution over time. So this is actually the uptake in the cancer cells like that. So it does work. The next thing, we were very ambitious. We just put into the humans. So at this time, we knew that iodine-124 MIBG, not exactly the same type of same molecule, but ours is a higher specific activity. But we knew at this time that there are studies using iodine, the 124 MIBG in 2 patients, in adult patients in the UK. That's all we could find. This is pediatric tumor. This is actually a child that when we did this, well, this is really the first time to use this MIBG iodine 124 for neuroblastoma. So I was very proud of it. We were able to really develop from the molecular level all the way, through the small animal imaging study and then the human studies. That's not, really it about. So now, when I was so much into neuroblastoma, we also wanted to find that what else we can do with neuroblastoma. So we also found out that neuroblastoma cancer cells do have a lot of somatostatin receptor. That's another word, I'm sorry about that, but this is highly expressed. This receptor is highly expressed in the neuroendocrine tumors, and neuroblastoma is behaving like it's also neuroendocrine, type of neuroendocrine tumor. So we know, that something like dual-modality. This is not really the real, can I say, real name for the real molecule. DOLA is a chelator. PET is just a shortened form of octreotide. Octreotide is a somatostatin analog. This molecule goes to where that receptor is. So I said that neuroblastoma tumors often, it's not 100%, do have a very good expression of somatostatin receptor. So there are a lot of somatostatin receptors there. So if you use somatostatin itself, this is analog, synthetic form of it, and then chelate it with radionuclides, you can see the tumors that express a lot of somatostatin analog, the receptors. So we knew that, but we wanted to do the same thing over. So we wanted to do some cell studies, and it's actually before, but this is actually animal studies I'm showing. And then we also did 2 different radionuclides, lutetium-177, gallium-68. In fact, the lutetium-177 dotatate is a commercial product right now. Okay? So it's about what we are looking at. A lot of people are looking at this one for adult cancer patients. People thought that lutetium-177 dotatate could be a very good drug. This is therapeutic drug that they went through clinical trials, and then they actually made it happen. So this is not commercial product, but not for neuroblastoma. They just looked at the other cancers because, of course, when the company develops something, drug, therapeutic drugs, right? They want to make it, available for treating people, but they have to make, of course, money. So pediatric cancer is not something that a lot of people look at for in terms of commercialization, because when I said about, okay, first of all, neuroblastoma, that expression of somatostatin receptor is not 100%. But at best, they can treat about 600 patients a year. You don't want to actually treat the children with cancer with the radionuclide that easily. You want to use that radionuclide-based therapy like the lutetium-177 one at the end, meaning that we can probably treat maybe 10, 20 patients a year. No company will invest any money into evaluating their drugs for this type of cancer. This is a very common problem. But anyhow, we want to do more studies to show that this actually works. So we did the therapeutic, but this can be also imaged. This is actually the lutetium imaging. This is gallium imaging. What I'm showing is that using the same animal model, we can show that both radionuclide, the radiopharmaceuticals, could have a good uptake in the tumors that we know that it has a somatostatin receptor expression. The reason I was doing that is also using just a very good imaging agent, which is gallium-68, dual-modality. Can we actually get some information about the therapeutic radionuclides, which is lutetium-177? My belief here is again that this gallium-68 is also quantitative PET imaging possible. So we can do quantitative PET imaging of gallium-68 dual-modality imaging. Can we actually get the quantitative information to predict something about lutetium-177? That is my research area. Something else I'm showing, another example of radiopharmaceutical. This is again back to prostate cancer. What we did was first, I think it's really first PET-MR. This is combined PET and MRI scanner. And we did the prostate cancer patients. We injected the fluorine-18 labeled fluorocholine. Choline metabolism is also correlated with a lot of cancer progression. So we could see the choline uptake is in the prostate cancer. Here, what also we did was that dynamic PET of fluorocholine. So we did some kinetic modeling. So we wanted to do as many quantitative metrics we could develop. We could derive from one imaging session. With MRI, we have some quantitation from MRI. This is dynamic contrast enhanced MRI. There are a lot of things here. So I'll put this here. But the thing I want to show is that we could do a lot of quantitation from our PET imaging using this radionuclide. And then here, what we did was that this information was also correlated with pathology. We did the same experiment. We recruited patients. We did quantitative imaging. Our hypothesis is that the imaging signal should be correlated with the actual pathology of the tumor. This is our newer effort. This is the F18 labeled molecule called the CPT-1057. This is just company naming. But this is the molecule that is targeting, I think, nuclear medicine's favorite target these days, prostate-specific membrane antigen, PSMA. You haven't heard about this probably, but that's what everyone's going after. But this is basically a new class of radiopharmaceuticals that targets PSMA. This is actually something different from, there are a ton of other PSMA targeting molecules out there. Ours is actually a little different. Why I'm saying ours? This is our in-house developed. It's not mine, but it's our UCSF homegrown type of imaging agent. This is also very good, the prostate cancer imaging agent. I can show you some example if you can read some of clinical images. This is a metastatic prostate cancer patient. This is a conventional bone scan using gamma camera, SPECT technique. Bone scan usually shows very sensitive detection levels of bone mass. There are some higher uptake of that bone scan imaging agent here, but it's a lot clearer. It's actually the same patient we're talking about. Another example, this is lymph node metastasis of prostate cancer right here. From prostate right there, this is a lymph node met. This is also confirmed from the CT signal. So what we did about this is, this is first in-human study of this molecule. First in human is that we actually recruited the patients who are courageous enough to get this unknown molecule into their body. And then why I'm showing this one, I did contribute. When we worked on this one, we really wanted to make sure that our imaging is as quantitative as possible. That is my contribution. I'm actually senior author for the paper. We just got reviewed, and then we are submitting to revision soon. Another imaging agent I'm showing for PET is gallium-68 citrate. I'm showing this imaging agent in prostate cancer. This is not targeting something like a PSMA, the favorite target of a lot of people these days. This is basically looking at ion metabolism. This, the citrate gallium, that's conjugation like this one, when it's injected to bloodstream, it basically breaks up. And then the gallium-68 is binding to the transferrin. Transferrin receptor is basically looking at where transferrin receptor is basically, we are looking at ion, the metabolism. So cancer does have also higher metabolism for ion. It really metabolize a lot of ion there. So this is very good ion metabolism imaging agent. And then our people are really saying that this has some very specific cancer progression pathway dependent. So we are very excited about actually doing some biology study with this imaging agent using PET. Again, if you have the biology study using PET, you can add biology with some physics there, which is also, once again, quantitative information could be obtained from PET imaging. Another example of using this imaging agent is looking at the liver cancer, hepatocellular carcinoma. This is the CT and then this uptake there. We could see that this also is taken up by not all the liver cancer. Again, this is about biology study. We are not really making this imaging agent to make a good detection of the cancer. We want to see where this citrate, gallium-68, the transferrin actually in the blood is taken up, and then we can make a sense of that the biology, cancer biology is amplified in that area of the cancer. This is also brain study. We are doing fluorine-18 labeled fluorodopa imaging of this gene therapy. Gene therapy. So this is a dopamine production pathway. We have L-tyrosine converted to L-dopa, converted to dopamine. So this is how dopamine in the brain is produced. So whenever people have a dopamine production problem, what big disease about that is Parkinson's disease. Or what if people do not have AADC? This is enzyme that converts L-dopa to dopamine. That is another kind of disease. Actually, there is a disease called AADC, this enzyme deficiency. This is pediatric disease. Some kids were born with AADC deficiency. So for Parkinson's disease or AADC deficiency, really the patients, they can have some improvement by having infusion of this enzyme, AADC, into their brain directly. So some of our people, actually originally from the LBL, they are doing gene therapy, basically gene delivery of containing AADC into humans. And then what we are doing, I'm doing, is that PET imaging of right here, fluoro L-dopa right there. If we do image it, the brain before and after this gene therapy infusion AADC, if you image with L-dopa, you can see actually the gene delivered, this AADC delivered, is retained after the surgery, after the infusion. So what we see typically is something like this type of imaging. So this is after gene therapy imaging, showing that the human putamen where the dopamine is actually, prevalent there. So you see the good uptake in the, the brain, like a human, the putamen area. This is a Parkinson's disease patient after the gene therapy of AADC. This is a kid with AADC deficiency. So this is also after the therapy. So I'm not actually showing the before the therapy. So the before the therapy, fluoro L-dopa uptake in the putamen encoded area was very weak. The signal is very weak because there's not much of AADC there. So now my slides about what we are doing about this one. So what I realized was that PET imaging really needs a lot of newer radiopharmaceuticals. No, we can do FDG. This is what everyone uses for cancer staging using PET. But the field of PET imaging is certainly about making, developing, validating new PET radiopharmaceuticals, because we can do a lot with these newer radiopharmaceuticals. Specific, targeted, that's what we care about. So that's why I showed all the slides with my PET imaging application with all this radiopharmaceutical in the red color. You know, it's not just you know, I didn't show like a 10 of them, but at least I personally showed, you know, the project I got involved, like 5 or 6 already, and counting more. So we have to team up with the radiochemists and the radiopharmacists, you know, to do any of the quantitative PET imaging, because doing something first in human, novel application, that's really fun. That's what I learned. Quantitative PET imaging could be actually better, but it's still very important to do, you know, in many PET imaging applications area, especially when we do PET MRI, especially when we do dynamic PET, we have to do some analysis that requires quantitative PET imaging techniques. We can also do some device development. In here, I could say totally the opposite to SPECT instrumentation. I said SPECT instrumentation, I felt that we have to make a really nice general purpose that can image brain, heart, and anywhere. But for PET imaging, now actually the current PET imaging technology is pretty robust. It's working very well. So people are looking at some niche area. One example is that you can actually make a PET imager for dedicated organ imager. Or the other extreme is that total body. This is a famous UC Davis project. Actually, they built the 2-meter long PET scanner to image the patient once. Okay, at once. That's what they've done. It's already built. If you haven't heard about that, they're going to do actually patient studies sometime soon. Sometime soon, meaning that their target is doing first patient early next year. That's their plans. So, I'm showing some of my work here. First in human is what I'm really passionate about. This is the dose calculation I made from the first in human radiopharmaceuticals of the PET imaging. So when you make a new radiopharmaceuticals for PET imaging, first thing you want to know is that how much of first of all you want to know kinetics, really kinetics of this radiopharmaceuticals in the body. You have to image it many times after injection. From that information, you can get kinetics of where it goes. From the kinetics, what you can do is that radiation dosimetry. So you can actually calculate how much dose each organ, each part of the tissue of human body can receive from this new radiopharmaceuticals. For existing ones, we don't care that much about it because we already have that kind of information. But anything new, we need to have this information. Who's gonna do it? So I'm basically the one who's doing all this and actually work at UCSF at the moment. I'm excited because I'm always happy about the new things. And then when we develop newer applications using existing radiopharmaceuticals, and then newer technologies or more quantitative way of imaging, many times that involves dynamic PET imaging. When you do dynamic PET imaging, then people want to do kinetic analysis. So that's something that we do a lot. You know, kinetic analysis is not just one size fits all. You need to understand kinetics. You need to understand the model. You need to know how to apply it. That's the type of research we do. Another thing I'm showing is that when we can do radiation dosimetry, this is one example. I think I'll go just first. It's actually very fast. So what I did was here, this is animal with the tumors, these neuroblastoma tumors in these mice. Okay, and then I was able to calculate how much radiation these tumors could receive from the certain amount of injection of radiopharmaceutical. From that, what we know is that how much we have to inject to have therapy on these tumors. Okay, these mice have tumors. Now we want to treat the tumors. We can make those tumors shrink. How can we do that? If we know how much dose we deliver for given, like a unit dose, we can calculate how much we have to inject to make the therapeutic effect, because radiation dose is the physics there, it's energy we deliver. So you have to deliver a certain amount of energy to certain cancer cells to be killed. So we derive that information. What we derived is that from our calculation, we have to inject at least about 2 millicurie of iodine-131, that's therapeutic radionuclides, to these animal models to have some therapeutic effect. This is exactly showing the data. This is actually tumor size growth over time. This is number of days. So 0th day to 25th day, this is size from just the unit volume, the doubling, like the quadrupling there. So when we injected the no radionuclide, therapeutic radionuclide, and 1 millicurie of iodine 131 MIBG into this animal, 2 millicurie of iodine 131 MIBG from this one, we see that 2 millicurie cohort has a therapeutic effect. It's not growing. It's growing later, but here others, okay, tumors are constantly growing. This is actually quite important because even for this animal model, we never had anything like this before. I looked at also all the literature publications about this one. And then people always used human equivalent dose to make animals to be treated. Meaning that, you have to inject a certain radioactivity per kilogram. That's how we, make a dose level for human injection. So for certain therapeutic radionuclide, that is already set. When you do animal experiment, how much you inject? For the normal people, of course, instead of doing this kind of experiment, it's very costly. That's okay. So they just use a human equivalent dose, convert it to animal equivalent dose, right? Just inject that amount. That is usually about like a microcuries, not like a millicurie. Of course, all the studies before this got, they never showed any therapeutic effect, using iodine 131 MIBG in neuroblastoma model. This is really first time we showed that. If we have this platform, what you can do is that, can we actually get some synergistic effect when we combine radionuclide with some drug? This is also done. Cancer patients go through all sorts of therapies. Many times they have a combination of radiation, chemotherapy, things like that. So we wanted to do exactly the same thing on these animal models. So here we know that 1 millicurie is not enough. What if we can add some drug that to make 1 millicurie is close to 2 millicurie of a radionuclide alone? This is kind of the plot I'm showing. We did animal experiments that using some drug support, we can make even lower dose to be more therapeutic than without the drug. This is very good platform to develop the combination therapy. Some quantitative imaging. So we did a lot of work on the quantitative PET imaging for PET MRI. Of course, correction is a problem, so we did some work on that. Final thing I want to say about the PET, the instrumented development. This is one concept that we want to build a dedicated brain PET scanner, because brain is the area that a lot of people are interested about. It's just an idea, conceptual design. Okay, I have just a few more slides and I'll be over. So this is the last thing I'm showing you, radiomics. 2 minutes? 1 minute?
2 minutes.
So I'll go directly to the point here. This is the cool thing I can say. So what we are really trying to do is that we want to do some deep learning for something that we know of, but can we make the model to predict future? So this is the study we just did, and then just the paper got accepted in press. So we got the retrospective data, basically the data acquired a long time ago. This FDG PET studies of the human brain. And then this patient have the history of either developing Alzheimer's disease later or not. So you have this course. Some people develop Alzheimer's disease later. Some people didn't develop Alzheimer's disease later. But earlier imaging using deep learning techniques, we could tell that almost 90% accuracy or almost 100% accuracy that we could classify the ones who developed the Alzheimer's disease versus who didn't develop Alzheimer's disease. This is prediction. So what I'm trying to say about this one is that there are a lot of enthusiasm going on about deep learning, machine learning techniques. But machine learning, deep learning, what they are good at is classification. That's what this really is doing. If you can do classification, but that classification could be actually the future occurrence of certain diseases. You study with the CT study, you study with certain studies right now, but the information there could be a good indicator for future disease occurrence. That's what we are working on. So this is really a lot of people, just partial credits. This is basically the list of people who contributed the content I showed you. I actually didn't explain everything that I was involved in. Of course, not 15 years is not a lot of time, but still, could be a lot of time. A lot of funding sources, right? That's what people have to do in this era of doing research. It's a picture. And this is where the mission bay looks like, the area picture of San Francisco around our area. Questions?
All right, thank you very much. That's an overview of many years of work, for sure. Questions? A few minutes. Should have for questions. Right.
For the quantitative imaging aspect that you're pursuing, are there any micro-dosimetric implants or markers that you look for to give you some reasonable comparison of your imaging results to conventional dosimetry?
No, this is more conventional dosimetry, but that's very actually good, timely question. So I happened to start working with someone in radiation oncology who's developing this microdosimetry chip for the alpha therapy. And what we want to do is that we'll do the chip-based dosimetry, direct measurement of alpha versus the imaging approach. We want to compare these two. Is there anything work like that done? And I think for some other therapeutic radionuclides or some other imaging radionuclides, probably yes, but I really do not know in the full detail. But for alpha, nothing. So we actually want to do that.
I have a question regarding, I have quite a few questions, but one, your CTT 1057 tracer for prostate cancer, that's PSMA. How does it compare with other state-of-the-art cases? So you show the results compared with the bone cancer, which is more really the conventional old way, but there are a lot of other like Gallium-68 labeling for PSMA. How does your approach compare to the other more state-of-the-art?
There's nothing different. We just like the effective more.
Because it's really impressive, of course.
That image is really looking very good because you just use the good scan.
One of the typical yes.
I didn't massage anything, but it's very different molecule. This is
sure.
But not the same core.
But you suspect if you have different, similar labels yet, like Gallium-68, which also we've done it.
Yeah.
Of course, UCSF. So that's ultimately is comparable. The
well,
specificity to the.
No, the study. This is just phase 1 study we just completed. Okay. Phase 1 doesn't really give you any sensitivity. We have some preliminary numbers, but not fully. But what we are seeing is that this is very comparable in terms of detecting the tumors we are supposed to see. Actually, a good thing is that it doesn't have that much of salivary gland uptake. So we thought that this is probably better for therapy because actually the other molecule, the urea-based PSMA targeting molecules, when it's labeled with lutetium and then actinium-225, it has a huge side effect of salivary gland dysfunction. But this one does have that much of a salivary gland uptake. So we hope that this could be better. But that's part of our phase 2, the company's phase 2 studies. We're just waiting for the research. It's submitted, and we're waiting for the grant to be funded.
Okay. Any more questions? Yeah.
Is anybody using transferrin to look at metabolism?
Yes. So it's memorial sloan carrying, the initiative, and Mike Evans, our faculty actually came from sloan carrying. So sloan carrying is actually making zirconium-89, the transferrin, IND filing, things like that. So they've done a lot of, the animal studies, but human studies we haven't done anything because it's collaboration between sloan carrying and us to do human studies.
Is zirconium?
It's zirconium-89. But gallium, the citrate is, our, really, it's a nice way of looking at similar effect. The literature really shows that chemically, biologically, once it's in the bloodstream, it becomes actually gallium-68 transferrin. But the transferrin uptake, you want to wait long enough, usually like 24 hours-ish. So zirconium does have so much benefit. Our images are showing 4 hours after the injection. The gallium-68.
Very good. Okay, thanks very much again.